10, A1 question 10. Do you have a question 10?
I do. Says, in a study of the accuracy of fast food drive-through, you have one restaurant with 40 orders that were not accurate among 342. So that is your population sample part is gonna be 40 orders, where your number overall is gonna be 342. Use a significance level of 0.01 to test the claim that the rate of inaccurate orders is equal to 10%.
Okay, good. So this is a great review question. So we're going to review hypothesis testing, where you always start out with a claim or idea about the population. So this claim has to do with the rate of inaccurate orders for the entire restaurant. So the entire restaurant is your population. So rate of inaccurate orders. Is 10%. And so this is a statement or claim about your entire population or the whole restaurant. But you're gonna make a conclusion about this population claim using an observation in the form of a sample. So this is your sample that's given. So you have a sample of 242 orders. And of those, the number that are inaccurate is 40. So X is the number of successes. In this case, success is inaccurate orders. And then the significance level is 0.01. Remember, the significance level is always 1 minus the confidence level. So if the significance level is 1%, that means the confidence level is 99%. Okay, so let's go ahead and go through the process of hypothesis testing that we talked about last time. There were step-by-step sequence of steps that we talked about. So what was the first step?
Restate your claim to where you have a null and your model.
Okay, so good. So ultimately, you want to identify two statements. One is the null hypothesis, one is the alternative hypothesis. Now, the model that we've been talking about is the null hypothesis. Okay. So, but formally, we want to identify two statements: null hypothesis and alternative hypothesis. So, those two statements are going to come from the original statement and the opposite to that. And the opposite to that statement we call the counterclaim. So the counterclaim is basically just the opposite statement. So what's the opposite statement to the rate of inaccurate orders is 10%?
The rate is not 10%?
Okay, very good. So the easiest thing to do is keep everything the same except for the equality or the inequality. So in this case, keep everything else the same except for this is, change it to is not, or is not equal to. So the counterclaim in this case would be rate of inaccurate orders is not 10%. So then, once we have the claim and the counterclaim, once we have these two statements, one statement will be the null hypothesis, the other statement will be the alternative hypothesis. We don't necessarily know which is which yet, so the next step is to convert each of these steps into mathematical statements. So let's arbitrarily start with the claim. So the rate of inaccurate orders for the population, we're going to use a variable P. That stands for the population proportion of success. Okay.
It's 40, right?
What is it?
40?
Oh, okay. So this is the proportion of success for the whole population. So this 40 is the number of successes, but it's for the sample. So we're dealing with a proportion of success, but for the whole population. So that has to do with this claim. So the claim is saying the rate of inaccurate orders for the whole population or for the whole restaurant is 10%. So if the claim is true, the mathematical statement is P equals 0.1. And let's do the same thing for the counterclaim, convert that statement into a mathematical statement. So the rate of inaccurate orders is not 10%.
So P is not equal to, so equal with the bar, 0.1.
Yeah. P does not equal 0.1. And so what's another way of saying P does not equal 0.1 in terms of inequalities?
P is less than 0.1 and P is greater than 0.1.
Okay, good. So P is either greater than 0.1 or P is less than 0.1. So P can be any number, such as being greater than 0.1 or it can be less than 0.1. Okay, so now that we have these mathematical statements, we're ready to identify the null hypothesis. So the null hypothesis is a statement that contains equality, or the equal sign. So in this case, which one would it be?
P equals 0.1.
Yeah, it would be the claim. So in this case, the claim where P equals 0.1, that would be the null hypothesis. So that would be HO. And the other one would be H1. So in this case, what was the null hypothesis? It only contains the equal sign. So that whole thing is the null hypothesis. But if you had a case where, for example, this had been P is greater than or equal to 0.1, then that would have contained the equal sign as well. So that would have also been the null hypothesis. But in that case, because we want to select the statement that has the equal sign to be the null hypothesis and model, we can only model a situation around equality. So we only, if something equals a number, we can model a situation around that one number. So in this case, if we had had this case that had the equal sign, but also had other stuff like greater than, then we would ignore everything else except for the equal sign and call that the null hypothesis. So regardless, the null hypothesis would contain a mathematical statement that only has the equal sign. So if you had had this case, P is greater than or equal to, you would have stripped the greater sign, and the null hypothesis would have just been P equals 0.1. Okay, so regardless, the null hypothesis is P equals 0.1. So you can think of it as the null hypothesis is an English statement, which is that the rate of inaccurate orders is 10%, or the mathematical statement is that P equals 0.1. And same thing for H1. It has an English statement, it has a mathematical statement. Okay, so that's the first step, identifying those two statements. What's the second step?
When do we find the tails?
Yeah, so good. So basically the second statement is to assume that HO is true. So there's not much action that is taken at this step, but this is actually the most important step because it's laying the foundation for everything else. So we're assuming that this statement is actually true. And this statement being true would imply that P has to equal 0.10. And that the rate of inaccurate orders is indeed 10%. So subsequently, we can visualize this assumption that P really does equal 0.10. And we're gonna visualize it by drawing a distribution of this variable. And because your claim involves this mathematical symbol P, which represents a population proportion of success, a proportion of success can be thought of as a number of successes out of another number of trials, so a proportion. So the variable here is the number of successes out of n trials. But n is our sample that we've observed, so n, our sample size, would be 40. So our variable would be the number of successes out of 40 trials. And successes would correspond to what?
Being an inaccurate order.
Very good. Whatever it is we're keeping track of, which is the 40 inaccurate orders, that's what we've been keeping track of, inaccurate orders.
But wouldn't the number of trials, because they got 40 inaccurate orders out of 342 from
Oh,
that
oh, okay.
restaurant.
Okay, good point. So yeah, I messed up on that respect, so it should be the number of inaccurate orders out of 342 total, not 40.
Okay. I'm not crazy, thank you.
No, good, thank you. Okay, so our variable is the number of successes out of a total number of 342 trials. So this is the visualization of this null hypothesis, which is assuming that P really is equal 0.10. So the number of inaccurate orders for the restaurant, we're assuming to actually be 10%. So if that's true, and you're observing 342 orders total, then how many inaccurate orders should you expect with the greatest likelihood?
If it was that, and just, spitballing it, I'd say 34.
Yeah, good. So 10% of 342 is 34.2, or 34 orders. So at 34, you're gonna see a bar whose height represents the probability of that observation. So this will be 34. And as you move away from 34 in either direction, the probability will get less and less that you observe that number of orders out of 342 if the rate of inaccurate orders really is 10%. Okay, so this is the visualization, and again, really this is a binomial distribution, because we're dealing with a distribution where each of the variables is the number of successes out of another number of trials, and each of these probabilities, or heights of the bars, represents probability of a number of successes out of another number of trials. So each of these probabilities can be found using a binomial probability, the NCX formula, NG's X formula. So this is a binomial probability distribution. And once you recognize it's a binomial probability distribution, then it's actually easy to find the mean and standard deviation of this distribution. So what's the mean?
So, n multiplied by p, but what's the number for p? Are we going back to?
Okay, good. So P, from this point forward, is assume that HO is true. So P is 0.10.
Check.
And again, that's a great question, because P represents the proportion of success for the entire population, the whole restaurant, which we haven't observed yet. We only observed a sample of the restaurant, not the whole restaurant. So that's why this assumption is so important, is because we need to assume that P really does equal 10%. So the mean is n times P. So N in this case will be 342. And then P, we're assuming to be 0.10.
Yeah, so multiplied by 0.1 is gonna be 34.2,
Yeah.
which is literally what that graph represents.
Yeah, literally what the peak of the graph represents. And then standard deviation will be, also have a shortcut formula, it's the square root of NPQ.
Where the, $5.5479.
Okay, good. Everybody else getting that? Okay,
Yes.
great. So now we have the mean and standard deviation of this distribution. The last thing we need to fill out in the distribution before we start incorporating the observation, 40 in there, is we need to decide how many tails are here. So last time we talked about the number of tails dictates whether alpha is distributed across one tail or two tails. So we said it was really easy to find the number of tails, always look at H1. So H1 was here from the first step. And then we look at the number of inequalities in H1. That'll tell us the number of tails. So in this case, we have two inequalities. P does not equal 0.10 means that P is either greater than 0.1 or P is less than 0.1. So you have two different inequalities, greater than as well as less than. So this is a two-tailed test. So that means that in this picture, you can go ahead and label two tails, one on each side. And so what this means is that everywhere in red, that represents a tail, and everything that's not a red, we call the body of the distribution, which is not the tail. And so the confidence level, being 99%, will always represent the area of the body of the distribution, the non-tail. So the body here will be 99%, 0.99. And the tails will always add up to what's left over, alpha, which is 1%. And since there's two tails here, both tails will combine to add up to the 1%. So each tail individually is how much?
0.005.
Yeah, so 1% divided by 2 is 0.5%. So that's 0.005 as a decimal. Okay, so this is the visualization of the assumption that HO is true, and P, the true rate of inaccurate orders for this whole restaurant, is 10% of the time. So this is the visualization of if we were to observe 342 orders, and we really have 10% inaccurate orders, then this would be the probability distribution representing the number of inaccurate orders we observe. So the most often is 34, and as we move away, it gets less and less. And we also see the body labeled as well as the tails, and that represents what's considered typical for this distribution. So everything in the body is considered typical, everything in the tails is considered unusual for this distribution. Okay, so this is the whole visualization of assuming that P really does equal 0.10. So now we're gonna go on to step 3. And step 3 is to answer the question of whether the observation is consistent with this distribution or usual in the distribution. So step 3 is answering the question of, is the observation consistent with HO being true? I'll emphasize it with consistent with the idea of HO being true. So this last part, the idea of HO being true, that's actually represented by this distribution. This is the distribution representing the assumption that HO is true. So we said that if you have an observation, in this case, x is 40. So let's say 40 is here. So I happen to draw it in the body of the distribution, but that's, right now, that's just a guess. Later on, we might conclude that it's actually in the tail. But if the observation is actually in the body, then the answer to this question is yes, the observation is consistent with this distribution representing the idea that HO is true. But if the observation 40 inaccurate orders had been in the tail of the distribution, either red area, then the answer to this question would have been no, the observation would not be consistent with the idea that HO is true. So this question can be answered only one of two ways. It's a yes or no question. So either yes, that implies that the observation is in the body of the distribution, or no, implying that the observation is in the tail. So based on what we talked about last time, how would we be able to quantify exactly whether or not this observation of 40 inaccurate orders is actually in the body or the tail?
So our significance level and confidence level, you can find how that equates over to the z-score, but what you're trying to find is the principal of the z-score itself, so you're gonna take x minus the mean divided by sigma.
Okay, very good. So our observation is going to have a test statistic in the form of a z-score. So the observation will have a z-score, and where each tail starts will also have its own z-score. So where each tail starts, we call the critical z-score, or z-critical. So since we have two tails, we have two z-criticals. So those are the z-scores that correspond to where the tails start. And then our observation has its own z-score that we call z-test. So this 40 will be z-test. So essentially then, we're just going to compare z-score to z-score and be able to exactly decide whether the observation is in the tail area or the body area. So let's start with z-critical. Z-critical is going to come from a chart. So we're going to use the z-score chart. Recall the z-score chart has a relationship between z-score and left area.
We know we get 99, we also know we've got 0.01 divided by 2, you get 0.005. The opposite of that's going to be 0.9950, but there's no real number. Well, actually, yeah, there is negative 2.575.
Okay, very good. So using the z-score chart, it has a relationship between two things. Z-score is the area to the left of the z-score. If you know one, you can find the other. So in this case, we're looking for the z-score, that's what we're trying to find. And if we knew the area to the left of that z-score under the bell curve, we could easily find it with the z-score chart. So this z-score we're trying to find, we know the area to the right of it is 0.005, but using the chart, we need to know the area to the left of it under the bell curve. So we know the total area under the bell curve is 1. So if the area to the right of that z-score we're looking for is 0.005, then the area to the left is 1 minus that. So this left area will be 1 minus 0.005, which is 0.995, 99.5%. And so we're going to use z-score chart, look up a left area of 0.995. So left area is a number in the middle of the chart representing left areas. Look for 0.995.
It'll be 2.575.
Good, and it should be 2.575. Okay,
Knowing that, the same is gonna be opposite for the other side, so you're negative as well.
very good. So that was z critical for the right tail. That was 2.575, but we know that the bell curve is symmetric, and because this is a two-tail test, the other tail will start at the same number but different signs. So this one will be negative 2.575. And if you didn't realize that, then you could have just looked it up. You could have looked up 0.005 as a left area in the chart, and the chart would have told you that the z-score is negative 2.575. So now we know the z-scores of where the tails start. So now we're gonna have to look at our observation and find its z-score so that we compare z-score to z-scores. So the test z-score will come from a formula. And last time we talked about how there was a class formula and there was a book formula, but either way, you're gonna get exactly the same answer. I think the book formula is more conceptual, and it's easier to understand and easier to remember, but you could use the book formula too, because when you're doing your homework only suggests the book formula. But I'll do the book formula so that when you see it on your homework, you know what's going on. Okay, so this is the book formula. So it's p hat. P hat is the sample proportion of success. The hat over it should tell you it's part of the sample. So what's that?
40 divided by 342.
You're good. So it's a proportion of success. So the number of successes is 40, but the proportion is 40 divided by the 342. 40. And then minus P is the true P for the entire population, the entire restaurant. So what would that be here?
0.1.
Yeah, good. So because in step 2 of hypothesis testing, we're assuming that P really does equal 0.1.
And then your square root is gonna be P multiplied by Q. Q is 1 minus P, so you'll get 0.1 and 0.9. And then it will be divided by the number of trials for this sample, which is gonna be 342.
Okay, P is 0.1. Good. So P is 0.1. Again, we're assuming that P equals 0.1, and Q will be 1 minus that, or 0.9. And then N will be the sample size of 342. Go and punch that in.
I got 1.045.
So as a check, you can also use the other formula we talked about, which we call is, so z-test is x minus the mean, which is NP, divided by the standard deviation, which is the square root of NPQ. So this is also another formula for z-test, but we'll give you the exact same answer.
So on that one, that would be X is 40.
Yep.
So N multiplied by P is gonna be 34.2.
Yep. So that was the 10% of 342.
Right, and then sigma is gonna be 5.5479.
Yep. So N is 342, P is 0.1, Q is 0.9. So either one you punch in, you should get exactly the same answer. So the formula we talked about in class, not only do I think it's easier to understand, because it uses the elements we talked about directly, the mean for binomial distribution is NP, the standard deviation is this, but also it'll be easier to punch in your calculator. It'll leave less room for error, because this square root will involve also division in here, and it's easy to make a mistake there. So you guys getting 1.045?
Yes.
Okay. So that number represents the z-test, or the z-score for our observation of 40. So that was the 1.045. Okay, so now that we have the exact numbers for the z-scores, we can compare them directly. If the right tail starts at 2.575, so z critical here, so the right tail starts at 2.575, but our z-score is 1.045, so that means our z-score is to the left of 2.575 on the number line. So because it's to the left of where the right tail starts, it can't be in the right tail. So the observation can't be in the right tail, but could it be in the left tail?
No.
No, because the left tail is everything to the left of negative 2.575, but we're positive 1.045, so we have to be to the right of where the left tail starts. So the observation can't be in the left tail and it can't be in the right tail, so therefore it's in the body of the distribution.
Knowing that you're at 1.045, you can't be less than 0, which is already 50%, so you're not even getting to the other tail.
Correct, so that's another way to think about the same thing, the same result, which is the peak is at a z-score of 0. And we're at 1.045, so you know that you're on the right side of the distribution anyway. There's no way you can be in the left tail. So the observation is neither in the left tail or the right tail. It has to be in the body of the distribution. So we're going to go ahead and answer this question in step 3 as because the observation is in the body, that yes, it is consistent with the idea that HO is true. So this is where we need to formulate a conclusion in words of what it should be if the observation is consistent with this idea that HO is true. So if you have one observation that is consistent with an idea, then what can you say about the idea being true for all cases? Can you accept the idea being true for all cases?
No, you don't reject it.
Okay, good. So the best conclusion we can make is fail to reject HO. And another way to say that, so fail to reject HO doesn't mean that you can never reject HO, even in the future. It just means for now, based on the evidence that we just observed, don't reject HO yet. So another way to say that is there is insufficient evidence to reject HO. So if we can fail to reject HO, what can we say about H1?
We also accept H1.
Yeah, good. So if we fail to reject H0, then we fail to accept H1. And another way of saying fail to accept H1 is there is insufficient evidence to accept H1. Okay, very good. Any questions, guys? So we always want to bring it back to the original claim, Because remember, that's what we started out with. We only started out with a claim and a sample to try to substantiate the claim. So we want to bring it back to the original claim, but the claim in this case was HO or H1.
H1.
So always go back and look at what we did in step one. So the claim was HO, right? So based on step one, how we labeled the statements,
Yes.
the claim is HO. And so we look at these two statements that are both true, either fail to reject HO or fail to accept H1, and then we look at which one pertains to our claim. So because our claim in this example is HO, then because we said fail to reject HO, we're gonna say fail to reject the claim. And I wanna give you guys, again, some intuition on what that phrasing means. So you have an entire spectrum of positions that you can take regarding any statement, in this case HO. Reject is on the far side, accept is on the other end of the far side, and then you have this entire spectrum in between regarding your position on this statement. So when you say fail to reject, it just means that you're ruling out this one case, but everything else is possible where you could take any position along the spectrum. All you're doing is ruling out this one position. So when you say fail to reject, it doesn't mean accept, which would be all the way over here. Fail to reject would mean any possibility on the spectrum. And again, it doesn't mean accept, but it's closer to accept than reject because it includes all these positions that are close to accept as well. So again, fail to reject doesn't mean accept, but you can think of it as leaning towards accept. Any questions? And likewise for fail to accept, same idea. You're leaning towards reject. Okay, questions? So again, if the observation is in the body of the distribution and it's consistent with this distribution of HO, then you end up with very weak conclusions. Fail to reject HO and fail to accept H1 are very weak conclusions. So ideally, when you're doing hypothesis testing, secretly, what you want to happen is you want the observation to be in the tail of the distribution. So you end up having strong conclusions. So if the observation had been in the tail, where your z-test had been like something that was greater than 2.5, then what would our conclusion be? If the observation had been in the tail.
The null is true, so accept the null or reject the claim. H0 is not true.
Okay, so we're gonna be careful. So if the observation had been in the tail of the distribution, that means that the observation is not consistent with this idea. So already we have one observation that is not consistent with the idea. So what can we say about the idea being true for all observations if already this observation was not true?
So it's not fail to anything, it's flat out reject.
Very good. So you can flat out reject this idea that HO is true because already you had an observation that was not consistent with HO. So you can flat out reject HO, and because you can reject HO, you can accept H1. So in this case, the claim happened to be HO, and so because we reject HO, we reject the claim in this case. So again, especially when you're first starting hypothesis testing, the part that is most confusing is the wording on these conclusions. So to help you remember, last time we talked about a simplified, absurd example with the sheep. And so let's remind you guys of that. So if you're ever in doubt, think back to the sheep. So remember, the whole point of what we're doing here is we're comparing an observation and seeing whether it's consistent with some idea. In this case, the idea happens to be of HO being true. But all we're doing is answering the question of whether an observation is consistent with an idea. So let's use a simplified example and say that our idea is that all sheep are white. And let's say that we have an observation that out of 106 sheep that we observe, all 106 are white. So in this example, is the observation consistent with the idea?
Yes.
Yeah, so in this case, yes, the observation is consistent with the idea. So just because our sample of 106 sheep are all white, can we conclude that the idea is true and accept the idea and say that indeed all sheep in the world are white, just
No.
because these 106 were white? Good.
No, because
So-
your observation is not seeing every single sheet.
Very good. So, because we have a limited observation that doesn't include the entire population. So, just because an observation is consistent with the idea, doesn't mean that we can just accept the idea. So we can't just accept the idea that all sheep are white just because these 106 were all white. So, the best we can do is hold on to the idea and don't throw it out. Hold on to it and keep having more observations and see whether the observations keep being consistent with our idea. And if all the observations in the world are consistent with our idea, then we can accept the idea. Or at least within a certain confidence level. If our confidence level is 99%, then if 99% of all observations in the world are consistent with our idea, then we can accept the idea. So the best we can do is hold on to the idea, don't throw it out yet. So the way we formally say that is fail to reject the idea. So that's if we have an observation that is consistent with the idea. We can't accept the idea. The best we can do is fail to reject the idea. In hypothesis testing, the idea under consideration is HO, so that's why HO is involved. And that again comes from step 2, where we're assuming that HO is true. That's the idea under consideration. Okay, so what if we had a case where we have an observation of, let's say, 102 sheep, and of those 99 are white, which means that the remaining are not white. The remaining, let's say, are gray.
Reject HO.
Yeah, so in that case, already you have an observation that is not consistent with the idea that all sheep are white, so you can go ahead and reject your idea that all sheep in the world are white. So this is if the observation is consistent. If the observation is not consistent, you can go ahead and reject your idea. So that's all we're doing here in hypothesis testing. If the observation is not consistent with this idea that HO is true, then we reject HO. Okay, any questions? So it all boils down to whether the observation is consistent with the idea or not. If it is, you reach one set of conclusions that happens to be weak. And if the observation is not consistent with the idea, it ends up that you have very strong decisive conclusions that you can outrightly reject HO. And so to emphasize this means that with this limited observation, this limited sample, you can go ahead and reject HO. So another way to phrase this, for emphasis, is that there's enough evidence to reject HO, or there's enough evidence to accept HO. Okay, any questions? All right, very good, guys. So that was a great review of hypothesis testing from last time. So this is a good point to segue into the next concept. So, I just want to give you guys a heads up. This next concept we're talking about is something called p-value. And p-value is something that confuses just about every student who learns it. And one of the reasons in particular for that is because the way that it's explained, especially in this textbook, is awful. And so it's not particularly a difficult concept, but for some reason it's explained very poorly in the textbook. So hopefully when we talk about it in class, it won't be so bad.
Section 8.2 or 8.3?
I think it's either 8.1 or 8.2.
Yeah, p-value is still in page one,
Yeah.
page 363.
Okay, so let's talk about p-value. So remember, with hypothesis testing, the name of the game is ultimately to answer the question of whether the observation is consistent with the idea of H being true or not. If it is, you reach one set of conclusions. If it's not, you reach another set of conclusions. And the way that we answer this question reduces down to whether the observation is in the body or the tail. So you go back to the previous step and decide whether the observation is in the body or the tail. And the way that we've been doing that is we've been comparing z-score to z-score. The observation has its z-score that comes from a formula, and where the tail starts has a z-score that comes from a table. So you compare z-score to z-score. But, and let's just remind ourselves of that. So, goodness. So let's just remind ourselves what we did before. We compared, to decide whether the observation was in the body or the tail, we compared z-test to z-critical. Alright, so z-test in the previous example, after calculating from the formula, was 1.045. And z-critical was 2.575. But when we compared our z-test to the z-critical, we had to know that that z-critical represented a right tail. So that everything to the right of z-critical would be inside the right tail. And because our observation is to the left of that, then we can't be in the right tail. And same reasoning for the left tail. So by comparing these two numbers, we concluded that the observation was in the body, and therefore we do not reject H. Okay, so that's what we just did. We compared z-score to z-score to determine whether the observation was in the body or the tail. So, but recall that you have a z-score table, that has a relationship between two quantities, z-score and area to the left of the z-score. If you know the z-score, then you can get the left area. And if you can get the left area, you can get the right area by subtracting from 1. So the point is that there's a relationship between the z-score of a data point, like let's say the data point is here. There's a relationship between the z-score of the data point and the area to the left of that z-score, or the area to the right of that z-score. If you know the z-score, you can find the left area and you can find the right area. So instead of comparing z-score to z-score, we can compare area to area using these correspondences in the chart. So let's look at our z-critical. Our z-critical already has an area that's associated with it that is common to us. So this z-critical, where the right tail starts, if you look to the right of it, it already has its own area that has some meaning to us. So the area to the right of z-critical is the right tail. Right? So instead of just comparing z-critical, we're going to compare the area to the right of z-critical. So the area to the right of z-critical is just the right tail. And because we're comparing the area to the right of z-critical, now, analogously, we're also going to compare the area to the right of z-test. So we're going to compare the area to the right of z-test versus the area to the right of z-critical. So the area to the right of z-test, of z-critical, or the right tail, has a total area of how much? In this picture. So the total right area. Yeah, 0.005. So that's going to be this 0.005, and then the total area to the right of z-test will be how much? So z-test has a z-score of 1.045. So how do we find the area to the right of that under the bell curve?
You convert it to its area, subtract that from 1, and then convert it back to the z-score and give it the answer.
Very good. So use the chart, use the z-score chart to look up for a z-test of 1.045, a z-score of 1.05, because it only goes to 2 decimal places. Find the left area that the chart gives, and then subtract from 1.
So you get 0.1469.
What is it?
0.1469.
0.1469. Okay, so this 1.1469 represents this right area of z-test under the bell curve. So if you look at this picture, that would be, if I shade it in, relative to z-test, this entire area to the right that would correspond to the area to the right of z-test. So the area, this total area in green, which represents the area to the right of z-test under the bell curve, is 0.1469. And the total area of the tail is 0.005. So this area in green is more than or less than this area in red?
It is more than.
More than. So that's consistent with this picture. This total area in green is greater than this area in red. And because it's greater than, that tells you that where the green area starts, the edge of that green area, that's our observation, that has to be outside the tail or inside the tail. So is it in the body or is it in the tail? So because this green area lies outside the red area, it can't be inside the tail. So based on this comparison, we conclude the same thing that we did before, which is the observation is in the body, and because it's in the body, we do not reject it. So same conclusion. Okay, any questions? Okay, so we were able to make exactly the same conclusion that the observation was in the body, but instead of comparing z-score to z-score, like we did previously and also in the last class, instead we compared an area that was relative to a z-score and also another area in the same direction relative to the z-score. So in this case, we compared the area to the right of the z-score to also the area to the right of the other z-score to make the same conclusion. And so how do we know to use a right area versus two left areas? So why didn't we compare the area to the left of z-test to the area to the left of z-critical? The reason for that is that if you look at z-test, the tail that is closest to z-test is a right tail because it's on the right side of the distribution. So the closest tail is a right tail. So you always want to find the area in the direction of the nearest tail. So again, because the nearest tail is the right tail, relative to our z-test, we're going to find the area to the right of our z-test because the nearest tail is the right tail. So that's why we ended up finding right area for both. So if our observation z-test had been over here on the left side, and this was a two-tailed test, the nearest tail would have been on the left side, and we would have compared left tail to left tail. Okay, any questions? And we'll do some examples of that. So we're comparing right area to right area. But now, based on the fact that this area of z-test has a greater area than the area of the entire tail, then we know that it can't lie inside the tail. It has to lie in the body and therefore do not reject HO. So this number is being compared to this number that represents the tail. But you notice that this number isn't alpha. Alpha is 0.01, right? So what relationship does that number have to alpha?
It is half of alpha.
It is half of alpha, right? So let's say that we actually want to compare the number to alpha.
So multiply it by 2, and you have alpha.
Very good. So
Wait a minute, is it 005 or 001?
0, 1. Thanks. So yeah, so alpha is 0.01. So we already reached the correct conclusion by comparing this number to 0.005. But 0.005 really doesn't have much meaning to us because it's not alpha itself. So if we want a number to compare directly to alpha itself and have the exact same conclusion, then this number on the left here needs to be multiplied by 2 to have the same relationship. So if you multiply the right number here by 2, we're also going to multiply this number by 2. So multiplying this by 2. Okay, 0.2938. So you notice, and again, we can reach exactly the same conclusion, because previously, the left number was greater than the right number, and now we just multiplied all sides of the inequality by 2, so you're gonna have exactly the same relationship. This left number will still be greater than the right number. And you have the same conclusion, that because this area is greater than 0.01 alpha, then you have the same conclusion that the observations in the body, or fail to reject HO. But the benefit of that is that this 0.01 now actually represents alpha. And the number that you use to compare directly to alpha to make a conclusion about whether the observation is in the body or the tail, that number that you compare directly to alpha is called the p-value. So the p-value is a function of the area in the same direction as the nearest tail. So you look at your z-test, and the p-value is a function of the area in the same direction as the nearest tail. And then, if it happens to be a two-tail test, then you multiply that area by 2 to get the p-value, so that you can compare directly to alpha. But what if we only had a one-tail test? Then what do you think you would do?
If you don't have the division of alpha for the one tail, you would divide that side by 2. If you have the z-score, you would subtract it and divide that by 2, because you're taking the side that it's pointing towards. And then plugging your value to equate your answer compared to what alpha was originally.
Okay, very good. So this was a two-tail test, so we ended up multiplying by 2. We ended up calculating this area and then multiplying by 2 because this was a two-tail test. And we needed to compare directly to alpha, not half of alpha. But if it was a one-tail test, and alpha is directly on that one tail, then once you get the corresponding area, then you're done. But another way to say that is you take that area and you multiply by 1 for one tail. But multiply by 1 doesn't change anything. So if it's a one-tail test, then you're done, or you can multiply by 1. If it's a two-tail test, then you multiply by 2. So let me summarize all of that. So the way that you calculate p-value. So there are 2 steps. One is relative to your z-test. But this process of calculating p-value generalizes not just the z-scores, but later on to chi-square distributions, the t-scores as well. So instead of saying z-test, I'm going to say the test statistic. Relative to the test statistic, such as z-test. Find the area in the same direction as the nearest tail. So relative to the test statistic. And then step 2 is once you find that area. So this was step 1, we found the area. And then step 2 was we multiplied that area by the number of tails. in the hypothesis tests. So that's what we did before. So step one was relative to this z-test, we found the area in the same direction as the nearest tail. And the nearest tail was on the right side, so we found the right area to z-test. And then because it was a two-tailed test, and we know it's two-tailed because we looked at H1, and we saw two inequalities in H1, and that told us it was a two-tailed test. And because it's a two-tailed test, in step two here, you multiply by 2 for the number of tails. So that's what we did here. And so this was the p-value. And the significance of the p-value is we use it to compare directly to alpha. Alpha was 0.01. That was given. And we compared directly to alpha, and because the p-value is greater than alpha, we know it's in the body of the distribution, and therefore you don't reject the region. But make a conclusion, we can call interpreting the p-value. But for now, we're just calculating the p-value, and we'll talk about interpreting. We'll summarize that later. But for now, this is just calculating this number, this p-value. And then what to do with this number, again, we'll elaborate on or summarize next time. Summarize in a second. So this example, this is the p-value, 0.2938. And we calculate it with these two steps. So let's practice on this. So let's say that you had a hypothesis test where z-test comes out to be negative 1.6. So it's on the left side of the distribution. Let's say that this is a one-tailed test, and specifically it's a right tail. So the question is, what's the p-value? So take a moment, based on what we just talked about, these two steps, calculate the p-value on your own or with your neighbor, and then we'll talk about it.
Feel like I'm missing some data here, boss. Alright, so negative, 1.6 is gonna be 0.0548. The other side of it, should be, 9452, but do I have that data right now? Cause all I have is the z-test, a tail on an end, and that my z-test is 1.6. Is there any other information that I can plug and play on that?
Yeah, so you don't need anything else, so you have all the sufficient information. So just follow these two steps.
since the left area net z-score is 0.0548, we have a right tail, means the right area. So when I do that, the right area is 0.9452, and since we only have one tail, that's our p-value.
Okay, very good, so let's talk about that. Okay, so your z-test is given as -1.6, and then the first step is to find the area in the same direction as the nearest tail. So this z-test here has a left area under the bell curve and a right area under the bell curve, but we want the area that is the same direction as the nearest tail. So the nearest tail turns out to be a right tail only, there's no left tail. So because of that, we want to find the area that overlaps that nearest tail. So relative to z-test, we want to find a right area. So we're going to look in the chart to find a left area, and looking in the chart, we're getting a left area of 0.0548, but the right area will be 1 minus that, or 0.9452. So that's the area to the right of z-test that overlaps this nearest right tail. And so that's step one. Step two is to multiply by the number of tails. So this is a one-tail test, so you multiply that area by 1, which is essentially not doing anything. And then, so the p-value is that number. So the p-value here will be 0.9452. Okay, any questions? Alright, so let's say that you had similar situation where z-test was still -1.6, but now you had a two-tail test. Go ahead and calculate the z-score.
So in this case, you would multiply that right area by 2.
Okay, so you still need to make sure that you go through both steps.
That's right, okay. So since z-test is closer to the left tail, we need to find the area to the left and then multiply that by 2.
Very good, so let's talk about it. So step one is relative to z-test, find the area in the same direction as the nearest tail. So in this case, since you have both tails, the nearest tail will now be a left tail and not a right tail like before. So essentially, you just want to find the area that overlaps that nearest tail. The nearest tail is the left tail. So in this case, you want a left area, which in the chart gives you as 0.0542. 48. And then step two is to multiply by the number of tails. So this is a two-tail test now, so you multiply this number by 2. So the z-score will be 0.0548 times 2, a little above 0.1.
Yeah, it's 0.1096.
Okay, great. So the z-score in this case will be 0.1096. Any questions? Okay, so this is calculating the p-value, given an observation, to calculate the p-value. So now what we'll talk about is after you've calculated the p-value, or somebody else has calculated the p-value and given it to you, how do you make the correct conclusion using that p-value? How do you conclude whether the observation is in the body or the tail, and whether to reject HO or not reject HO? So this will be interpreting the p-value. So interpreting so this is interpreting the p-value once it's already been calculated. So let's say that we have the case, so we have two more cases. Let's say the p-value is less than alpha. So a picture of that would be so remember, alpha is the area in the tail. So for simplicity, let's say it's a one-tailed test. So this represents alpha. So let's say p-value is less than or equal to alpha. And so let's say the p-value, remember the p-value is a function of the area in the same direction as the nearest tail. So let's say that the observation had been here, and so the p-value is here. So the p-value is the area that overlaps the nearest tail. And so in this case, that area will be less than alpha. So this will be the p-value in this case. So the p-value, the area overlapping our nearest tail for the observation is in green. Alpha, the area of the tail itself, is in red. So in this case, the p-value is less than or equal to alpha. So is the observation in the tail or the body of the distribution? Yeah, so that means if the p-value area is less than the tail area, that means it has to lie inside the tail area. So this means that the observation must be in the tail, and therefore the conclusion must be, so if the observation is in the tail, like we said before, then what's the conclusion?
You reject it.
Yeah, reject HO. Okay. So if the observation is in the tail, then you reject HO. So all you have to do to make the correct conclusion using the p-value, is compare the p-value to alpha, and if the p-value is less than or equal to alpha, then you can reject the null hypothesis. So there's a cute saying to help you remember this, which is, if the p-value is low, the null must go. So when we say that the p-value is low, that means it's low relative to the comparison with alpha. So if the p-value is lower than alpha, the null must go. So you reject the null hypothesis. So that's if the p-value is less than or equal to alpha. Let's do the case where the p-value is greater than alpha. Remember, the p-value is the function of the area overlapping the nearest tail. So if the p-value is greater than alpha, it's going to look something like this, where this total green area is greater than the red area. So that's if the p-value is greater than alpha. And if that's the case, that means that this observation here is inside the body or the tail of the distribution.
It'll be in the body.
It's in the body of the distribution. Okay. So this means that the observation must be in the body of the distribution. And if it's in the body of the distribution, then what's the phrasing of the conclusion that we make?
Fail to reject.
Good. Fail to reject or do not reject HF. Okay. And so you can use the same cute saying that we used before. If the p-value is low, then all must go. So what you can do is you can insert nots. So if the p-value is not low, then the null must not go. So that means you do not reject HF.
Program trying to do the other ones, like the p-value fly,
Okay.
the null must fly, but that's not, and it's, that can be misinterpreted because you're failing to accept or not rejecting. People confuse it, so this one works a lot better.
Excellent. Yeah, that's actually a great point that I meant to mention, which is if you look in your homework or even if you go to the learning lab, they'll teach you the other cute saying of if the p-value is high, the null must fly. And that sounds really cute, but it's kind of useless. Because it's not clear what flying means. If the null flies, does that mean that you allow it to happen? Does that mean you accept it? It's just not clear. And this phrasing needs to be very specific. It needs to be very technical. And so do not use that wording. So this is good wording. So use this one saying, if the p-value is low, the null must go. But if it's not low, just insert nots in front of these two clauses. So the null must not go means that you do not reject the null. Okay, any questions? Okay, so you see these two sides of the p-value. One is calculating the p-value, and when you calculate the p-value, you have to accommodate for the number of tails. So if it's 2 tails, you have to multiply it by 2. But once you've accounted for the number of tails, when you go to interpret using the p-value, you don't have to worry about that. You always just compare to alpha, regardless of the number of tails, when you're making an interpretation using the p-value. So, and this is the benefit of using the p-value, is once you calculate using the p-value and incorporate the number of tails, then when you go to interpret the p-value, you don't have to worry about the number of tails anymore. You always just compare the p-value that was calculated by you or given to you and compare it always to alpha. And alpha is always 1 minus the confidence level. It doesn't matter how many tails there are. Okay, so it turns out that because of that convenience, where you can always make a conclusion with the p-value comparing only to alpha, this is where the payoff comes in. And this is why the p-value ends up being the de facto standard for how people make a conclusion with hypothesis testing. So really, in real life, people don't compare z-test to z-test, or z-test to z-critical. People give you the p-value, and you can compare to alpha to make the conclusion. So let's look at an example. Okay, so let's say that you're reading a scientific journal and the researchers give you a p-value at the end that they've already calculated. And let's say the p-value they calculate is 0.03. So let's say that you reading this paper, you have a confidence level of 95% confidence. That means that the conclusion that you want to make, you want to have 95% in that confidence in that conclusion. So the question is, based on only this information, what would your conclusion be regarding the hypothesis test of this research paper? Regarding the null hypothesis.
Would be to reject the null hypothesis,
Okay, what's that?
because the p-value is less than alpha.
Okay, excellent. So because this p-value has already been calculated, all we have to do is interpret using the p-value. So all we have to do is take the p-value and compare it to alpha. If it's less than alpha, that means, so then, once we compare it, we just use this cube sample. So the p-value is given, all we need is alpha. So alpha is always 1 minus the confidence level. Confidence level is 0.95, so 1 minus 0.95 is 0.05. So in this case, if you compare these two, the p-value is indeed less than alpha. So if the p-value is low, the null must go. So in this case, reject the null hypothesis. So it turns out that rejecting the null hypothesis is a very strong conclusion. So that tells you that if you're a researcher, then you would want your p-value to be low or high.
You would want it to be high.
Well, you would want a strong conclusion at the end, no matter who reads the paper, right? So if you want a strong conclusion, that means you want your p-value to be low so that the null can go, so that you can definitively reject the null hypothesis, as opposed to fail to reject the null hypothesis if the p-value were high, right? So as a researcher, you would secretly want your p-value to be low, so that it ends up being lower than any possible alpha. Okay, so let's say that you have the same research paper, same p-value, but this time there's another person reading the paper who demands a higher confidence level. So let's say that they demand a confidence level of 99% confidence. So what would that person's conclusion be regarding the null hypothesis?
You fail to reject.
Okay, very good. So if the confidence level is 99%, then alpha is
0.01.
0.01. And because the p-value is not low compared to alpha, then the null must not go. So you do not reject HO. So fail to reject HO. And you notice, the reason we failed to reject was this p-value was not low enough compared to this alpha. Had it been even lower, then we would have been able to reject with this confidence level. So as a researcher, you would want your p-value to be as low as possible. Any questions? So this example shows the rationale for why people use the p-value comparing two z-scores. So people use the p-value so that all you have to do to make the proper conclusion, regardless of who's reading the paper, is just report a p-value, and whatever confidence level people want to have, they can just compare this to their own confidence level, and they can make the proper conclusion. Or they can compare it to their own alpha using their confidence level, and get the right conclusion. Now, what if this idea of p-value had not existed? Then what would the researchers have to report so that you can make a conclusion?
They have to give you a percentage with a margin of error and the confidence level behind it to basically make their claim and prove it.
Yeah, so-
they give you
so-
the entire confidence interval.
Okay, good. So instead of a p-value, if this idea had not existed, then they would have to give you their test statistic, z-test, right? Because with z-test, you can compare z-test to z-critical, where the tail starts. So with the z-test, you can compare that to Z critical. But what would you need to find Z critical?
You need to know if you have one or two tails.
Yeah, you would need to know your own confidence level, which is easy, but you would need to know also whether you have one or two tails in order to look it up in the chart and find the correct area that matches the Z critical you're looking for. So that's actually a lot of work, to think about how many tails there are, and go back to the study to see how many tails there are, and also have to have a chart with you to look up the correct Z score, Z critical for your confidence level. So finding the Z critical in order to compare to the Z test that's given is a lot of work and it's cumbersome. If you compare that to the p-value, all you need to compare this p-value to is alpha. And alpha is easy to find. All you have to do is take your confidence level in your mind and subtract that from 1, and that's alpha. And it doesn't matter how many tails there are. You don't have to go back to the study and see how many tails there are. Alpha is always 1 minus the confidence level. So this comparison of p-value to alpha is much easier than the comparison of z-test to z-critical. So that's why the p-value is much more convenient, and that's why it's used much more commonly. Any questions? All right, that's it, guys. Have a good day. So the homework on 8.1 and 8.2, originally that was today, but basically we just talked about the same material, reinforced it, so I'll push it back to next time, to tomorrow. Tomorrow night.
Things make sense now, I can say that.
Good,
Like, I
good.
got through the majority of it, but when I got to question 10, I just like, question 10 was beat the devil. I'm like, they're missing something here, I'm not sure what
Yeah,
I was
yeah.
missing, so, thank you.
Yeah, of course.
I didn't know if we were going to 8.3 or doing more stuff today or not, or, and it talked about different parts about what you're trying to identify, and it's taking the word problem, reading it, and figuring out specifically what they're asking. They're kind of clear with what they're asking for, if they want a population, a mean average, or your signal for the deviation. So that one wasn't hard to figure out. The whole sales thing, like read the book, saw the definition, looked at the changes, that wasn't hard to figure out.
Okay.
Then we got to the end of it, and I'm like, where, like we just,
Yeah.
Albuquerque, like, where?